Hello, welcome back everyone for this last day of the machine learning with Python. I remind you that you have access to the website here containing the slide, etc. So you can copy this address in your browser, or you can go on whatever searching engine you want and just hit GitHub. GitHub QCBCollaboratory, and should be enough. You go in the first link here. You go on the machine learning workshop W17. You go in the third day here, and you will have access to the slides over here, and you will need later you will need this synthetic dataset, so please be sure to have this tab open in your browser, and we are going to use it later. Okay, so what are we going to do today? So we are going to do regression and non-supervised learning, so linear and non-linear regression and supervised learning, and I will bring a little bit of conclusion at the end of this workshop. Okay, so first of all, be sure to have Jupyter open. So for that you need to open your Anaconda navigator, right? So I remind you, you can hit Command space and begin to type Anaconda if you are in Mac. If you are in Windows, you need to hit the start button. It should be available, or you begin to search it in the search bar. And if you are in Ubuntu, maybe you need to open terminal and begin to type Anaconda navigator, and should open like last time. Okay, so now you go in the folder you were last time. You go in document here, machine learning workshop, and you can begin to create a new workshop. Okay, so a new notebook. So Python 3 notebook, you open it here. You can make the title like Machine Learning Day 3, something like that. And don't forget to import NumPy as NP and pyplot as PLT, okay? Otherwise it won't work. Import NumPy as NP and import matplotlib.pyplot as PLT, okay? Okay, so we have our machine learning notebook ready. Linear regression. So what is a linear regression? So I guess you're already familiar with that. I've talked about it in the last days. So basically you want to predict, rather than what we did yesterday, to have like a classification, that is to say yes or no answer. It's more smooth, it's more continuous answer you want to give. So the typical example, you have cells, you have some characteristics of the cell, like the length, the width, the smoothness of the cell, etc., and you want to predict a continuous value like the volume, something like that. So typically you want to draw some lines here to make the prediction. Okay. So the goal, in fact, is based on the features, what you have here, the length, the diameter, whatever. You want to fit the parameter alpha, beta, gamma, and v0. So that is linear regression. So if we are linear regression, that is to say that the target is linearly depending on the features. What does it mean? Is that the target is going to be a linear composition, so it will be just the feature times a certain parameter alpha here, that remains to be determined by the fitting, plus the diameter times a certain parameter here, and in the end you just have last parameter just to have the ordinate at the origin. When everybody is equals to 0, what does it mean? Okay, so the goal of your machine learning model is to fit the parameter alpha, beta, gamma, and v0 in order to have the best possible prediction from the volume based on the features. Okay, that is a linear regression. And yeah, so pretty much let's do it. Let's see how you do it. So we are just going to create a simple data set that represents nothing in particular. It's always good to create a data set yourself, that you know what is the good answer to find to, and then after that you begin to use for the first time an algorithm. It's good to know if you have well understood what the algorithm is doing, and if it train yourself on data set that you know everything about, rather than and after that apply it to data sets that are real data sets. Okay, so that's that. I'll come back here. Yeah. So let's create this data set. So we're going to create a data set with 100 samples, and linear coef will be the linear coefficient. I'm going to set it 0.5. The intercept is going to be 2.2. Big X, capital X, sorry, will be the x-axis of all my samples. So I'm going to randomly choose the x-axis of my samples. They will have just one features for now. So X is going to be the features, and to be np.random. So random is a sublibrary of NumPy that deals with random numbers, and random, that sublibraries as a function which is called randoms. This is why I call random.random. They give me back numbers between 0 and 1 randomly chosen, and in fact it's an array. So if I do that in samples, it will give me back an array of this size here, so 100 number between 0 and 1. So I take 100 number randomly chosen between 0 and 1 and give me back a NumPy array. So since it's between 0 and 1, I want just to have between 0 and 10, so I just have to multiply by 10. So that will be a random number between 0 and 10. And here I'm going to put some error. So you have X, which would be the features. You will have the target that will depend linearly on X, plus a little bit of an error that is representing some fluctuation around the more precise answer. So the error is going to be pretty much the same thing here, but it will be, I want to have between minus 0.5 and plus 0.5 to have a little fluctuation here. So the way you do that, since this guy here gives me back an array of numbers between 0 and 1, I just have to subtract 0.5 to have between 0.5 and minus 0.5 and 0.5. Okay? So let's just check that. We are going to print the minimum of X, which should be close to 0, right? Because X is an array of numbers between random numbers between 0 and 10. And the max will be around 10, right? And we'll print dot mean. So the error dot mean should be around 0. Okay. So yeah, it's what we have. We have something close to 0 here, something close to 10 here, and something close to 0 for the error mean. Okay. Okay. So here we are going to create our target, which is linear coef times X, so capital X, plus the interception. Okay, so that will be just a linear dependence, and we'll just add the error. Okay. Okay, so I've created Y, and I'm going to plot my data. plt.plot X is a function of Y. No, Y is a function of X, I should say. I will going to plot a circle, so I just put like the syntax is just a string with a small O. It's not a 0, it's an O. And I can specify the color. So here I'll specify the color to be specific. Of course you can just put blue or whatever, but here just to show you, you can put I think it's red, blue, and green, or RGB, red, green, and blue, sorry. So here I'm just going to put 0, 2 of red, 0, 6 is between 0 and 1, 6 and 1 of 0. So it will be mostly green, mostly blue, a little bit of green, and very few red here. plt.x label, so I'm going to put the x label, which is going to be the feature. and the y label is going to be the target, and plt.show at the end. Okay. Oh yeah, I need to put, so you don't need to write writing down, it's just for you to better see what I'm I will increase the font size for you to better see on the video. Okay, and plt dots. Okay, so it should be better, so I can remove that guy now. Okay, that's better. You have the feature, the target, and indeed it seems to have a linear dependence. Okay. So we do it properly. Of course, that's a data set that we created ourselves, so it does not pretty much make sense to since we know the real answers, it does not make sense too much to split between the training and testing data set. But let's do it just to have a good practice. So from scikit-learn model selection, import train selection here, train test splits. Okay, and I'm going to see x. So I remind you that in scikit-learn you don't. So if I look at the shape of x here, it's 100 rows. It's a one-dimensional array with 100 rows. I remind you that in scikit-learn the way it should be, it's number of rows and number of features. So it should be a two-dimensional array, and an array with 100 rows, one-dimensional array with 100 rows only, is not the same thing for a scikit-learn as 100 rows and one column, sorry. So we need to change that guy here in order to be sure to have the two-dimensional array, the number of rows, and the number of features. Here is just one. Okay, so is why you have this line here. So I'm going to say that x is just going to be x.reshape, and here the number of samples, because it's the number of rows of x, and just one column. Okay, if here I just look at what is the shape, is 101, which is a different object. Okay. Okay. So x train, x test, y train, y test is going to be train test split. Go to the line, x y test size. 33. So yesterday I put shuffle to be false. I don't put it here. So shuffle is just to when you make the train test split, it randomly choose the one which are taken for the train and the one for the test. Yesterday I put it to be false because everybody of us had the same data set, and if in order to have kind of the same result, it was better to put it here. Here, as you all created your own the data set and they were different for everybody, it does not make sense to put shuffle here. You can put it if you want, it does not matter. Okay. Okay, so we have separated, and we are going to apply our linear regression. Okay, so you know the drill. There is a sub-library called linear model, in which you have a function linear regression. You have plenty of parameters here. For example, you have this one, fit intercept. If you think that the origin at 0, for feature 0, you should have target 0, you can put this guy to be false. That is to say that the last parameter here, here v0 will be assumed to be 0, and will only fit those parameters here. But in our case, it's not the case, so we'll keep it as it is, normalize, whatever. Plenty of options. Okay, so since you look at this graph here, you can say that the linear regression seems to be a good option. So let's do a regression like that. And in order to do it, you just need to import from scikit-learn.linear model. Sorry, import linear regression. Okay, and we're going to create a model which is a linear regression. And we are going to fit the x train, y train. Okay, So we fit the model, it has created a model, etc. And we are going to plot what is the prediction of that model, right? So here I'm just going to create an X array, which will be all the number, it will be number for which you want to test what the model is predicting. So for each dot of lowercase x array, I'm going to look at what is the prediction for the model. So X array will be all numbers between, numbers between 0 and 10, and I want 100 subdivision. You know, linspace is being the end and the number of subdivision, and the end is included. That is the only example where I know of where the last number is included in Python. And the Y array will be the prediction made by the model of X array. Okay, so it will be model.predict. And here, be careful, you need to reshape it, otherwise you will have an error. If I just do x.shape, it will tell me, oh, there is an error. Sorry, it's X array. Here, I should have put. It tells me that there is an error. I should have expected a 2D array. I got 1D array. Is the same thing as before when I was doing. Where was it? X.reshape. Yeah. It's when I did that, it's exactly the same error. So here I just put reshape in the good shape. So the shape is 101. Okay, and that works. And we are going to plot the prediction all together with the data set. So we're going to copy that, to paste it, and going to print it. Okay. Oh yeah, we should put just train here. Okay, so we're going to put the train, and we are going to put the plt.plot X array, Y array, and we are going to do it like R for red, and the dash is just to say a line, a thick line, and just going to change the line width to be 3. Okay. See what happens. Okay, so it seems to be a pretty good prediction, right? So I get the features, the dots are the from which it is trained, and the line is the prediction. Okay, cool. So you can have a look at the model and give you plenty of information, in particular what is the coefficient it found and what is the interception it found. So if you look at the model.coef underscore. So I'll remind you, the underscore indicates that it's something that is determined after the fitting. So it's an attribute that is determined after the fitting. And you can look at the intercept. Okay. So the coef, in fact, is an array that may contain several coefficients. Here we just have one feature, so it determines just one coefficient. But if we had several features, I will see in the following slides, you would have several coefficients. Okay, and the intercept is the interpretation is just a number here. Okay, so we were supposed to find 0.5, with which we created our data set. He's indeed around 0.5, and the interception, I don't remember, it was 2.2, right? Yeah, so it was 2.2, and it found 2.3. So that's okay. It was pretty good. Okay. Okay, so how do you know your model is predicting well? So you can use the performance matrix, which is the R2 score. So here, if I go, sorry, okay, go back here, and go here. So what it does is use this formula. So it looks at the difference between the prediction and the real one. It put a square and put it in a way that R2 score is between 0 and 1. So if it's close to 0, it means that the regression is very bad. it has very poor confidence in what it's doing. If it's close to 1, it means that it's perfectly aligned with the line it has drawn. So it gives you an idea. You can look at the exact formula. It's not complicated. It's just to be here. You see the difference between the prediction and the ground truth. Square sum, and you divide it by something else, and 1 minus that, and give you the answer. Okay. But basically, if it's close to 0, then it's bad. If it's close to 1, it's good. Okay. So how do we have that? So you can just use model.score x test y test. Yeah, 96%, 97% of accuracy. You can remark that I tested on the testing data set to be sure. So, okay. Okay, so we have done linear regression. Now we continue with polynomial regression. You might think that is something much more complicated than the linear regression, but as you will see, we just have a small trick, and it will be exactly the same thing as you will see in just a few slides. So, what is linear regression? You have several features like x, z, and you want to determine the best coefficient beta 1, beta 2, and gamma to fit the feature here. And if you want to have a polynomial regression, you need to have x, like x squared, x3, x to the power of 3, in order to x cubed, sorry, in order to have a regression. So in fact, what you can do is just to create new features. Rather than having z here, you can replace it by create out of thin air new feature, which is just x squared, and make a linear regression with that. So in fact, mathematically, linear regression and polynomial regression is exactly the same thing. The only difference is that you created a feature with just the square or the cube or the power, whatever you want, of the first feature here. So in fact, that is still considered as a linear regression, even if we use polynomial features. Okay. So how do you do that? So yeah, first of all, we are going to create new data sets, which is going to be polynomial, and going to use our linear regression on that data set. Okay. So for that, as always, since we don't have exactly the same shape, the difference between two-dimensional array with 1 column and one-dimensional array. So I just need to change a little bit the error here and just to reshape it. Here it will be the length of e, which is the number of elements in this vector, and just 1 column. The new y is going to be the linear coef times x. Okay. And here we're going to add a quadratic term, so of a polynomial factor, a term of degree 2. And the coefficient is just going to be 0.15 times x squared, so it will be squared. I'm going to still to put the intercepts, and I'm going to add the error that now has the good shape. Okay. We are now going to plot the results, so the x, y, o. Okay, o for the circles. The color is the same. Color is equals to 0.2, 0.6, 1.0 here. Okay, I'm going to plot the x label. Going to be the feature. Oh, what are you doing here? Come back here. Feature. Target. plt.show. Okay. Yeah, just a typo here. Okay. Y label. Okay, so the feature, the target, and it seems to be quadratic, right? Okay, so I'm going to use that data set to create our model. So as always, we are going to split it. So we just pretty much copy this line here, take here, and we are going to create an array, two-dimensional array, with the first column will be x and the second column will be x squared. We are going to create a new features out of thin air, which is just the square of the first feature. Okay, so features is going to be, for now I just say that it's going to an array of zeros, so just zeros, and here I put the shape, so length of x train here, and just two columns. Okay, and here I'm going to fill it out. The first column, so all the rows, just the first column, so the one at x0 is just going to be x train. For x train, since x as a new two-dimensional array with just one column, you need to say I select all the columns and just have the first all the rows and just select the first column, otherwise it will give you an error. And I do exactly the same for the second column of features, that is going to be x squared. Okay, and I'm going to print the features. Okay, so it should be 67 because it's the number of x train, the number of rows in x train, and two columns, and each of the column will correspond to the corresponding feature. So the first column will be x, and second will be x squared. Okay, and we are going to fit our linear model. Model is equals to linear regression. I'm going to fit it. Features y train. Okay, I'm going to print the model.coef and the model.intercept. Okay, so here we have two features. So we have two linear coefficients, the first one and the second one. So the first one corresponding to the first feature and the second one corresponding to the second feature. This one is for x, so it was 0.5, and this guy is around 0.15, which was also around the term for the second degree polynomial, the coefficient of the second degree polynomial, since it's good. And this guy was supposed to be 2.2, so that's okay-ish. Okay, so that's the intercept. Sorry, here. Okay, so cool. What about that? Okay, so let's plot it. So basically, we can make a big copy paste of this guy here. So I already defined x array, but let's do it once again to be sure. So x array, I choose it to be numbers between in space between numbers between 0 and 10 and 100 subdivision, and y array is going to be the prediction. So it's going to be x array times, so this guy here is a list of lists, so model of coefficient contain all the coefficient. I want the first element here, so the first element will be just this list here, since it's a list of lists, so I put 0 here. And I want the first element here, I want this guy here, I put another 0. Okay, okay, plus I can go to line because I put parentheses here, so I can go to a line without any problem. It will be pretty much the same thing. The thing is that it will be x squared times the coefficient that at position 1. So model.coef underscore 0 is going to be that list, entire list here, and I take the one at index 1, it's this guy here. Okay, and I add the prediction of the intersection, so model.intercept. Yeah, okay, otherwise the rest should remain similar, if I'm not mistaken. Okay, Okay, so that's the prediction. Seems to fit pretty much the data, right? Okay. So basically I explained how to make the polynomial fitting. It is, it's pretty much the same thing as linear fitting. And you can also imagine things for exponential fitting and logarithms fitting. In fact, it's the same trick. You come back here and you just create out of thin air a new feature, which is going to be the exponential of x, and then it could fit pretty much if you take the exponential, of x, it will fit you like a log, and you can take the log in order to fit an exponential. Those kind of tricks are very, very useful to create out of thin air the features that you want in order to make the correct fitting. Okay, so yeah, so okay, so for now we have applied these regressions on known datasets, since it's us who build it. Let's apply it on some dataset that we don't know anything about. And okay, so for that you need to access to the dataset which is on the website. So I ask you to keep this tab open, and if you go below here, you can click here, synthetic dataset used for polynomial regression. Click here. So that's just, as you can see, a two-column, a text file with 2 columns. So very, very easy. Just save it. So hit save. Okay, yeah. So you can hit, Command S should be enough. You go in the same place you are, the same place in which there is your data set, and be sure to have a .dat at the end, so not that.txt or something. So save it here. Okay. So normally once you have done that, on your directory you should have this file accessible here. So be careful, the first column is the feature, the second column is the first column is the target, and the second column is the feature. It can be intuitively in the other way around. Since it's a very simple file, you see it's very, very simple, we can use the numpy.loadtxt here in order to load the data. Okay, so data is equals to np.loadtxt here, and the name of a file. So you can begin to write the name down and hit tab key, and it will work, because it also look at what are the file in your directory. So you begin to write a string, it will search in the file of your directory if it's here, and allow you to say not to write everything. Okay, shift return, it worked. I'm going just here to print data.shape. Okay, so 50 rows, 2 column, and we are going to save it to make an array with the features and an array with the target. Sorry. So y origin, which is going to be the target data, all the columns, column index, all the rows, sorry, and column index 0. The same thing for x here. So that's the origin. You need to split it. So I'm going to do test y test is going to be train test split. Go to the line, x origin, y origin, test split, test size, sorry, 20%. And be sure to have shuffle to be false, so that everybody has the same as the same data set. Okay. Okay, so we have done that, and we're just going to plot plt dots plots x y as small circles. Oh, sorry, it's a small o here. plt.show. Okay, so it looks like that. and we are going to make a linear regression. So the very basic one. So the model is going to be a linear regression, and we are going to fit the data. Okay, let's do it. So we fit x with the features x with the target y, and oh, comes an error. Okay, can you see what's happening here? So if you go at the very end here, it tells you that it expected 2D array and got a 1D array instead. So something went wrong. It's always the same story for the features. The scikit-learn wants a 2D array with the number of rows being the number of samples and the number of columns, the number of features, and x here is just a 1D array. So we need to change that. And yeah, so basically if you look at the shape of x, it's 40 rows, and it's a 1D array with 40 rows. And we need to have number of rows and number of features here. So we are going to redefine x to be the reshape of x with the number. So x shape 0 will be this guy here. I remind you that the tuple, so that's a tuple here. So you can imagine just being a list of numbers. So if I take access to x.shape 0, it will be this guy here. Okay, so we have 40 rows and 1 column. Okay, and if I print then the shape of x, the new shape of x is the one we want, 41. Okay. Okay, so we are going to see what's happening. So here, be sure to define coefs. It's because we are going to fill those lists, coefs and degrees. I'm going to fill it one after the other. I will increase the degree of a polynomial. So I'm going to put some information into that each time we will test one of the regression. Okay, so degrees, coefs. Okay, let's say that. Okay, so my model is a linear regression. Okay, I'm going to fit it with .fit x and y. I'm going to have to add the degree. So degrees, it will be degree dot happen. So the degree is 1. We try to fit just one-dimensional polynomial. Polynomial of degree 1. And also we are going to add 1 to say that the fit is made with a polynomial of degree 1. We are going to add the coefs. So the coefs is going to be, so here I'm going to look at mp.abs, so absolute value of the model.coefs, so that will be there. So you have plenty of values in the coef corresponding of each degree of the polynomial. Here's just 1 because it's just one-dimensional array, one degree polynomial. But in the future work we will make with higher degrees. So we are going to have all the absolute values of the coefficient, and we'll just take the mean of all of them. Okay. Okay. X array, so it's like just before. We are going to define np.clean space between 0 and 1 with 100 here. I need to reshape it, otherwise it won't work. Export array.reshape the length of X array with just one column, and Y array is going to be the prediction via the model of X array, and we are going to plot it. pt.plot X array, Y array as blue circles here, and we are going to, oh sorry, that is not blue circles. So first I will plot the data. So the data is x, y. So I will plot them as blue circles, and I will plot the prediction as a red line. Okay. prt.show. Okay. So basically that's the prediction. Of course, it's very bad prediction. We are indeed underfitting our data. So we are going to increase the degree of the polynomial. So we basically do the same trick as before. We are going to put it together. So the easiest way to do it. So before we just create a zero, plenty of zeros, and we fill it one after the other. I remind you that we have something to, when you have a 1D array, then you can just copy paste, you can make a 2D array with this 1D array by just using the syntax np.c underscore square bracket, and here you put all the 1D array that you want to concatenate in order to make a 2D array, which each column corresponds to each of the 1D array you put here. Okay, so let's do that. X poly for x polynomial, np.c underscore square bracket x and x squared. Okay, print x poly shape. Okay, so it has 40 rows and 2 columns. Okay, and let's do that. Okay, so basically we just make a big copy and paste. We change just 2 things. So here it will be x poly rather than x, and we append the degree 2, and normally all the rest should be almost the same. Yeah, there is x array poly here. Okay, so I'm going to change this guy here, np.c underscore x array squared, yeah, poly, and I'm pretty for poly, and I think that's okay. Okay, so that's okay. So it seems a little bit better, but not that good still. So we are going to increase the degree of the polynomial. Okay. So to do that, rather than writing it down, making big copy paste and changing that, we are going to create a small function that from an array gives you back a 2D array, each column corresponding to 1 degree of the polynomial, and the degree will be given here. Okay, so just a small function, def get poly. It will be my array, so it will be just an array that you give as a parameter from a function. Degree, it will be the maximum degree you do it. So I'll remind you, since I'm defining a function, you need all those guys here to be indented in the same way, otherwise Python won't understand what's happening. Okay, so I'm just going to here write results. It's going to be just for now an array of zeros, and the shape of this array will be my array dot shape 0. So normally this guy here will be more or less 1D array, 1 column. And you will take this first shape, so it's just the number of rows, and the number of columns is going to be the degree here. And for each column, so degree, so j is going to be 0, 1, 2, etc. up to degree -1. Okay, keep that in mind. And I'm going to say that the results, so the gth column of results, so that's all the rows and the gth column, it's going to be my array. So here just put label, because sometimes we'll use this guy to be a 2D array with just 1 column, and sometimes we'll use this guy as being a 1D array with that many rows, and sometimes there is some bugs with that. So in order to put everything together, I just put revel. So that is to say that even if it's 2D array with 1 column, I will transform it into 1D array only, and it's going to be to the power of j plus 1, y plus 1, because it begins from 0 up to degree -1, and you want just the one just after that. So it was, there is +1, and at the end, don't forget to return the result. Okay? Result, yeah. So let's test it. We are going to create x poly, which is going to be get poly of x with a degree of 5. Okay, and I'm going to print x poly dot shape. Okay. So it's 40 rows and 5 columns, is each column corresponding to 1 degree of x, right? Cool. So once we have that, we can make the copy paste here. So let's try it with the degree to be 5. So here I'm going to put the degree here, okay, and I will import x poly, which is going to be get poly of x and degree 5, and x poly array, no, x array poly, sorry, array poly is going to be get poly of x array and the degree, sorry, degree is to be d here, so we just have to change this guy in order to change the degree. Okay, so I do that, that's the same. Here I'm going to append the degree here. This does not change. The linspace, I can remove it because it's already defined before. This guy is already defined, so x array poly is defined, and y array is going to be the prediction of x array poly, and I'm going to do that show. Okay, this is web for 5. Oh, so 5 seems to be a good degree, right? Maybe try it with degree 19 here. So basically, since we did everything with just depending on d, right? We just need to change this d here to say 19. Okay, so that is basically overfitting. You are taking too much advantage of the data. Okay. So let's have a look. So how do you know if you are overfitting with your regression? Of course, in real data sets, you have much more features, so it's not easy to see if you are overfitting. A way to know if you are overfitting is looking at the coefficient. And we are going to plot all the coefficients. So what I put in coefs. So in coefs, I put the absolute value or the mean of the absolute value of all the coefficients. It gives you an idea of how the coefficients are behaving, all the coefficients together. And we are going to plot it at, we are going to plot them. So we are going to plot them in log. The x-axis, so we can use, rather than using log, rather than using the function plot, we use the function log, so it will be in log. The x-axis will be all the degrees, so we test it on degree 1, degree 2, degree 5, and degree 19, right? So it's what you are going to put, go back here. Right. It's what you are going to put at here, so it's to be degrees as the x-axis, and the y-axis will be coefs, which is the mean value of the mean of the absolute value of all the coefficients at each time. I'm going to plot it as a blue circle with dashed line. Okay, I will change the marker size, for instance. Marker size to be 8, for instance. plt.y label average coefficient. Yeah. So to be precise, it's the average of the absolute value of the coefficient, but okay. And the x label is going to be the degree. Okay, plt.show. Okay, so basically you are increasing from a degree of around 1, 10, something like that. You are very much increasing the degree of the polynomial. Here you have like a billion high polynomial, so a coefficient for the polynomial. So it's a sign that you are clearly overfitting. You are trying to make very steep turns when in the polynomial. Okay, so it's a bad sign. So basically, it's a way to know that you are overfitting. So there is a solution against that, which is using what we call regularization. So here, what you have is, in fact, when scikit-learn is making its regression, it tries to minimize a function. So basically, that would be the prediction of the polynomial. B is going to be a vector of coefficient. So we try to find the best coefficient here, to have this polynomial here that is the closer possible to the label. Okay, so that is a polynomial depending on all the coefficients that are in the vector B, and here so that's the prediction made, and here you subtract the real data, and you put it at the square, to have just positive data, and try to minimize this guy here. So in fact, it's just an optimization problem. Mathematically, it's just an optimization problem, quite simple, in fact, mathematically. But since we minimize this function, maybe we can, and when we do that, basically, the coefficient may be very, very, very high. So since we want to, at the same time, minimize this function and minimize all the coefficients, to have for coefficients which are not too high, you want to predict the best to minimize the function. So in fact, you can just add a term here saying, okay, at the same time, I want to minimize this term here, but I also want to minimize the coefficient. Okay, so the way I do that, so that's just the sum of all the square value of the coefficient here, this guy here. And I will just put a parameter, so divided by 2, don't care about it. But alpha will just be what is the trade-off between minimizing the coefficient and minimizing the closeness to the data. Okay, so it will try by regularization to minimize those two functions all together, and the trade-off will be given by the hyperparameter alpha, also called metaparameter. Okay. So it is what we say by regularization. So with that you can use a very high polynomial, but with an additional term which is try to keep the coefficient in good order of magnitude. Okay, so you know the drill. There is a function which is doing that, which is called ridge in linear models. And we are going to use it, and as you can see here, it has one parameter called alpha here. Okay, so let's use it. Okay, so from scikit-learn.linear-model import ridge here, and it's import. Yeah. Okay. So we are going to create a model called ridge alpha with just at first alpha to be 0, model dot fit x poly y. So this guy here I have 19. It's a 90-degree polynomial, so it's quite high. And we are going to do plt plots x, y with blue circle, take blue circle, and that's all. And plt.plot the x array, the prediction of the model, so model.predict from x array poly, and we'll plot it as a red line here. plt.x label x I plt.show. Okay, let's do that. Okay, so it's not that good, and typically that's the sign of a too large alpha. As you can see, it's not taking too much advantage to the data. So maybe we can increase alpha to have a better fit. Okay. So let's change it. Let's choose, like, for example, C, E, alpha to be 0.001, and let's plot it. So that is much better. And as it's noted here, we are using a 90-degree polynomial, and still we have a very good fit that is not overfitting. Okay. So it's quite a powerful tool to use regression, to use regularization for regression, and you can pretty much fit plenty of things using that method. Okay. Okay. So yeah, you don't care because you're on the internet. But if I was in class, I would ask for the people to look at the survey. Okay. Okay, so now I will talk about unsupervised learning. So, sorry, for now, either in the regression or the classification, what we did is we had some data which has been annotated. That is to say, from those training data, we know what is the answer that we have to find. And the unsupervised learning is a very different approach. Is to say, okay, you just have data we took, and by yourself, you ask the computer by yourself, try to find some structure inside, to try to find some cluster or things like that. So you don't have like right or wrong answer. You have nothing no target to find. You just have to find some structure underlying into the data. So this kind of when you're comparing, for example, to text, to translation, you want to find some common features of things like that. This kind of application. So I'm going to talk about k-means algorithm. Is typically that you have data, you want to find some cluster of data, and some where the data are gathered with each other. You can even have more complicated stuff like hierarchical clustering. That is to say, like to find to try to reconstruct some kind of phylogeny or something like that based on the data. So having small cluster and gathering cluster together, etc. So I will talk about this algorithm, which is quite simple and quite straightforward. And if you need more algorithm specific to your problematic, I will have a word at the end of the workshop. So how k-means is working. So k-means works like that. You have 4 steps. So the first step is just the initialization. You in the data set, so he's in 2D, but you have to imagine that is in the same dimension as the number of features. You are going to put some dot that will represent the center of the cluster. Okay. Then you will assign. So it's what we do here. So here I've assigned randomly the cluster center. And then what I will ask the algorithm to do is to assign the points to the nearest cluster. So for example, all those points here are the nearest from this center here. So I'm going to color them into orange, the same as the cluster here, and I do the same for all the data. So these points here, these data are closer to that point here, and these data are closer to that point. Okay. Then I update the position of the center of the cluster. That is to say, I'm going to put each point, each center at the center of mass of all the dots. So you know what is the center of mass? It's like the mean position for all those dots is around here. The mean position for all those dots is around here, and etc. So you're going to change the position of the cluster, and then you move the center of the cluster, and then you repeat. So basically here there's just a slight change. This dot, which was before closer to that center, is now closer to that center here. So I'm going to color it in green, and then I update it, and then here nothing changed because all the dots that are closer to that center are already the colored in good color, and the same here and the same here. So basically here the cluster has stopped. The algorithm has stopped, but you repeat those points as long as it is necessary. So it's quite a simple algorithm. It seems quite just by looking at it, quite reasonable. The only thing is that with k-means you need to specify the number of cluster a priori. That is to say, here we said, oh, there is going to have 3 clusters, so please find 3 clusters. There's other algorithms that have tried to find other kind of clusters without assuming the number of cluster. Okay, so let's go back here. Yeah, so there is an algorithm to do that. So it's from scikit-learn.k-means cluster, sorry, the library cluster, k-means, and here you have the most important cluster, which is the most important parameter, which is n cluster, that is going to be the number of cluster to find. Okay, so we are going to apply it to real data sets. So as I told you, we did it that Monday. We use a data set already built in scikit-learn, which was the breast cancer of Wisconsin data set. Here we're going to use another one, which is the iris data set, which is very well known. You can go on that Wikipedia page. It has its own Wikipedia page. So this data set is its own Wikipedia page. It has been done, I think, by one of the founding fathers of the modern statistics, at least statistics applied to biology, with Fisher. So you might have heard of him, and yeah, basically he built his data set. So basically there was 3 species of iris, and measure for each of the samples what is the diameters of the petals, what is the length of the petals, things like that. So he had like I think 4 or 5 features, and for 3 different species, which looks a little bit like each other. Especially those 2 here looks like a little bit like each other, and we are going to use that data set. Okay. So how do we use that data set? So it's the same thing as the first day, if you remember. So there's a sub-library in a sub-library of scikit-learn, which is called dataset, and we are going to put import load iris datasets. Okay, it works. So iris. Sorry about that. Hit print screen button is what it has done that. So iris dataset data load iris. Okay, and we are going. So if I do that, I can like look at the type. What is the type of iris dataset? So it says that it's something called utils bunch. Okay, but in fact it has an attribute called data, and that is ND array, which will represent all the features, and you can have even the shape. Okay. Oh, sorry. Print the shape. So the shape is a tuple. So it's 400 rows and 4 features. Okay, 150 samples. So 150 rows and 4 columns for 4 samples. Okay. And we are going to plot it like in 1 dimension, so like the dimension number 1 and dimension number 2. So plt.plot, we are going to put iris data.data. So here I take all the rows, and I take just the first feature. sorry, it's the feature at index 1, so in reality it's the second one because we begin to count from 0 to here. I'm going to put, okay, and I'm going to plot it as small circles, okay, and I'm going to show. Okay, so it looks like that. The dimension number 1, dimension number 2. If you want to know what corresponds to each features, I think that you can have that, no, features name, yeah, what that is. So the first one would be the sepal length in centimeters, sepal width, petal length, petal width, okay. And so here we plot this guy here as a function of this guy here. No, this guy here as a function of this guy. That is the x-axis. That is that. Sorry, that is the y-axis. Okay. Okay. So, and let's use k-means for that. From scikit-learn dot cluster imports k-means. Okay. So k-means is going to be k-means, and here I'm going to specify the number of cluster to be 3, and it needs to have s clusters. Okay, it's the same syntax as before. You define your estimator, and then you use it and you fit it. The only difference here is that since we do not make supervised learning but unsupervised learning, here you just need to put just the features because there is no target to find. Okay, so it will be just iris.data here. Okay, it has made its own fitting, and we are going to look at what is cluster k-means dot predict iris data, and I'm going to print the shape, yeah, the cluster shape. What are the clusters shape, and I'm going to put cluster itself. Okay, so it has 150 rows, so that will be an answer, and here you have all the prediction that is made. So here just, so the class is 0, 1, 2, okay, for 3 class. So it says that the first element of data will be classified as the class number 1, etc., etc., etc. For this one here, it will be classified as a class number 2. This guy will be classified as a class index 0. Okay, so just the ID to which it belongs to. Okay, you might have something different because since the initialization step is random, maybe you have all the zeros that are replaced by ones and all the twos that are replaced by ones, etc. It doesn't matter. Maybe when we plot the color, the cluster will have different index. But since the initial condition, the initialization is randomly made, so it might be randomly made another way in your computer. Okay, so let's visualize what it corresponds to. So I'm going to have index 0 that is going to be, I'm going to put some parentheses, maybe it will be clear. I will look at the object clusters, which is an array of 150 rows, and I will look at each of the rows from which there is index 0, so it will be false everywhere except where the index is 0. I do the same, sorry, I do the same for the index 1 here, tick, and the same for index 2. Okay, so that will be arrays of true and false, only the true word corresponding to the corresponding index. Okay, and then I can access to my data set using that. So we are going to plot them with 3 different colors. PLT plots. So here I'm going to plot iris data.data which is going. I will only select the rows which are corresponding to the one which has been predicted to be of index 0. And I just take the column at index 1. And I do the same with this guy here, but at column at index 2. I'm going to plot it as circles, so small o for circles. And I can make the color here is going to be blue. And I will just specify the marker size to be 4. Okay, and I do that for all the different index. So here is going to be the same thing with index, the one that I'm going to plot it as black, and here the one at index 2 that I'm going to plot it as red, and I'm going to put an X label, which is sepal width centimeters, and that's the petal width in centimeters, and I'm going to show it. Okay, Y label. Okay, that's better. Okay, so here I was looking at the same representation as you. Maybe you have something slightly different because the blue or the red are blues or the black are red or whatever. But it should be something like that. Okay. So yeah. So summary of k-means. Since you need to specify, maybe it's not optimal in your other problems because you might not know how many clusters there is. In that case, you can use other algorithm like affinity propagation. Yeah. So k-means is the simplest algorithm. There is another algorithm which is very close to k-means, which is k-median. Maybe you can imagine what it is. It's much less sensitive to the outliers because what it does when it does the algorithm, rather than putting here at the center of mass, it puts at the median element. So if you have like one individual which is here, the center of mass might tend to be around here, but the median will be still around here. So it's less sensitive to outliers. So maybe you can be interested in using k-medians instead of k-means, but the algorithm is kind of the same. You just change you don't put the center of the cluster at the center of mass, but at you take the median elements of your features. Okay. Yeah. So yeah, ancestor is different than classification. You don't have a right or wrong answer. You just have to find some structure. So it's something different than the supervised learning, than the classification in the supervised learning. If you want really to find to predict categories associated to the samples, prefer use the some algorithm that we see the other day. Okay. Okay. So the principal component analysis. So maybe you already know about that. You can put it under the umbrella of the unsupervised learning, even if some people might say it's not unsupervised learning, but it's just that you have some data and you want to reduce the number of features. Like you might have 30 features, and in fact only very few of them are explaining what's happening. If I take the example of the cells, maybe the length and the width of the cell are very linked with each other, and having two information can be just sum up just into just one. So it's what is doing the principal component analysis. So it does not take into account any target. So in that sense, it can be gathered under the umbrella of unsupervised learning, and it tries to reduce the correlation between the different features. And so I'm going to explain it a little bit more mathematically. not too much, don't worry, but just to give you an insight of what's happening. So for that, the correlation is based, so correlation intuitively between two dimensions, two features, is something that this one is highly depending on the other one, like the volume and the length of the cell are highly depending from each other. Okay, so this correlation is based on what we call covariance. If you have two features, y and x and y, the covariance will be defined as the mean of the product of the two minus the mean of the first one times the mean of the second one. Okay, if the covariance is very close to 0, it means that the two features are not correlated at all. If the two are very high, then they are highly correlated. For example, if you look at the data sets like the number of people taking the metro line in New York, in New York subway, and the probability to rain, there is a high covariance. When it's raining, people tend to take the metro and the other way around, right? Okay, so we have, like you have a data set with plenty of features, x1, x2, x3, and you can create what we call a covariance matrix, which is just the covariance between each of the features. So here's the covariance of x1 and x1. We can also call that the variance on the diagonal, but here will be the covariance of x1 and x2, and here the covariance of x1, x2 and x1. And if you look at this formula, if you switch x and y, it gives you the same result, meaning that the covariance of x and y is the same as the covariance of y and x. And in terms of the covariance matrix, it just means that it's a symmetric, positive definite symmetric matrix, which has good properties mathematically, and that in particular it can be diagonalized. Okay, so what does it mean intuitively? So here I give you the example of two features which are really highly correlated, and you can see that there is kind of two there is two preferential dimensions here. If you go in that direction, you explain most of the variance. In the second dimension, you explain a little bit of the variance. And so basically just making the diagonalization is just to find, you make a rotation into your features to find the best the best new orientation in which most of the variance is explained. So here you will have the first dimension that explains most of the variance, and the second one that explains the rest of the variance. And in that orientation, so what I call that the PCA1 and PCA2 is just a combination. PCA1 is just a combination of all the features, and PCA2 is the a combination of all the other features, and they are squared. There is a orthonormal base. And in that, PCA1 and PCA2 have no correlation at all. In terms of if you take the covariance matrix of this guy here, it would just have the variance on the diagonal and 0 everywhere else. So it's what we do by doing the diagonalization. We try to find the best orientation in which each dimension explains most of the variance, and each dimension don't have any correlation with each other. Okay, so it's the idea of the PCA. Okay, so as always, there is a function in the scikit-learn for that, scikit-learn.decomposition.pca, and we are going to test it. Okay, from scikit-learn.decomposition imports PCA. Okay, and here I'm going to create my own data set that I'm controlling in order to test the PCA. So it is going to be np.random. I would choose to have 200 rows and 3 columns, as if there was 200 samples and 3 features. Okay, So they're just an array, 300 lines, 300 rows, and 3 columns, and randomly chosen with numbers between 0 and 1. And I'm just going to change it a little bit. I'm going to set that the column at index 2, so the third column, will be exactly the same as the one of index 0, the first column. Okay? So, of course, they are perfectly correlated since they are exactly the same. Okay? Okay. So let's print the covariance matrix. So it will be 3 features, so it will be 3 by 3 matrix, so we can plot it easily. np.covariance. So because NumPy has different standard as scikit-learn, NumPy is expecting the array to be transposed. So to have 200 columns at just 3 rows. That's what it's expected to have in order to make the covariance. So in order to do that easily, there is an attribute called t. So here's an array. You can use .t as it is an attribute. It's just the transposed version of x. So if I just can just show you what is xt.shape. It's 3 rows and 200 columns, and if I don't put the transpose here, 200 columns, 300 rows and 3 columns. Okay, so I'm going to print the comatrix, and since it's always nice to visualize a little bit what's happening, there's a function called matShow for matrix show, and that can plot the matrix in a visual way. So is what I'm going to do here. I'm going to plot the covariance matrix here and plt.show. So basically, this matrix here representing the numbers with the redder it's the higher it is, and the bluer it's close to 0. What you can see here, so that is expected to be relatively high because it's the variance, so the variance of each feature, and you can see the dot here, meaning that the covariance between these features and this one is very high. Okay, you can see that it's symmetric as we expected, at least much higher than the covariance between 0 and 1, and the covariance between 1 and 2, which is very, very small. Okay, so what it means here is that the features at index 0 is highly correlated with the one at index 2. Okay. Okay, so let's create the PCA. So just a PCA object. I'm going to feed it with the data, which are x. Okay, and here you can put the explained variance ratio. So as I told you here, making the diagonalization makes have the first feature to have the most explained variance of the data, and the second one the second more expressed variance. So here the first features is explaining most of the variance. The second one, the second PCA is explaining a little bit less. If you are more features, then it will be decreasing. Okay. So we are going to know what is the percentage for each feature that explain the variability. Okay. So PCA.explain variance ratio, which is with an underscore because it's done after the fitting. And I say that the first feature of the PCA is explaining like 69% of the variance. The second one is explaining 30% of the variance, and the last one almost nothing. Normally it should be 0, but the algorithm is not precise enough, but I mean it's minus 10 minus 32, so it's pretty much 0. And you can also access to what we call components. So components will be what is the dimension of this vector here. Okay, so if I look at rather in that situation, so I wonder what are the coordinates of that vector that will explain most of the variance, the first PCA, and what is the component of that vector, etc. Okay, so here, since we have a 3-dimensional feature, it will just a 3 by 3 matrix here. So this guy here, the first column here, is going to be the coordinate of the first feature, and you can look at this one here, the last PCA, which is exactly the same. It's just like you have a minus. It means that they are autonomate, that is to say that it makes a square angle here, and the last one. So all those three are having square angles with each other. Okay, so that's the components of each vector. Okay, so let's plot a little bit the same as before. It's just we are going to plot not the covariance but the covariance of the transformation. Okay, so X transform is going to be PCA.transform of X. Okay, and here I'm going to plot exactly the same thing as before. It will be just X transform. Transform, and I forgot an R here. Okay. Okay. So what does it mean? So here you can already remark that all the diagonals are 0, meaning that there is absolutely no correlation between all of these. The highest correlation is for the first one, the second one are having a little bit of correlation, and last one are having almost 0. So it will be like the minus 35 here. Okay. So basically, what I want to say here is that if you have a data set with very few correlation over there, it means that maybe all the relevant information are just gathered into the few first component analysis, and you can just shorten the data set to the first features rather than having 30 features. You can just gathering into the first 2 PCA, 2 or 3 first PCA features in order to build your model, and we are going to do that just after that. Okay, so we're going to apply the PCA on the breast cancer model. So for example, I'm going to do the data sets. I'm going to import load breast cancer. Okay, and B cancer going to be the object of load breast cancer object. Okay, so I'm going to load that. So I remind you, it's the dataset we used on the first day, and we are going. It says like 30 features or something. So let's have a look of. Yeah, first of all, it's true. A good practice is to make the splitting. So X tests, Y test, trend test split, go to the line, B cancer dot data, and B cancer dot target. Test size, and just do not shuffle it so that we will have the same results. Okay. Forgot the comma here. Okay. So I'm going to create. So yeah, if I look at the shape of X, it has 30 features, and we are going to do the PCA and just select the first two, the few first PCA features that will explain most of the variance. So let's do it. We're going to create a PCA object, okay, and we're going to make a fit with X here, okay. So let's plot the explain ratio. PLT.plot, PCA dot explain variance ratio with circles and dots here. PLT dot y label could be explain variance. And for X, it will be principal component number, and it is the X label plt.show. Okay, so we cannot see it, but we can see already that the first component analysis explains most of the variants. It's around almost to be 1, and we can just specify what is, we would just want to look in log scale for the y-axis. So for that we just have to put plt.yscale, scale, and you can put a small string with log. And if you do that, then you can see log scale, and you can see that's just around like the 5th one is already explained just 10 to minus 5, 10,000th of the variance is explaining that the 5th one. So basically, most of the variants explain that the very first component analysis. So rather than considering the 30 features, you can just consider maybe the first 3 ones in the PCA, and even the first 2 here as the principal component analysis. Okay, so let's do that. XPCA, PCAs, PCA.transform X. Okay, and here I'm just going to select not the 30 components of the PCA, but just the first 2. So I'm going to select all the rows and only the first 2 columns, so from the beginning up to index 2 without including index 2. Index 0, so that will correspond to I think it was the malign. 0 is malign and 1 is benign, or the other way around, whatever. So that will correspond to the one which are malign, let's just say, and this one, index 1, would correspond to all the index for index 1. Okay, I'm going to plot it. plt.plot x PCAs index 0, 0. Okay, so I'm going to plot its first dimension of the PCA, then the second dimension of PCA. I'm going to plot it as square, and the color is going to be red. Okay, so just do it like that. I'm going to do the same thing with the one of index 1. It will be circle, so a small O here, and it will be blue. Okay, and plt.x label is going to be PCA1 and PCA2 for the y label, and plt.show. It really does that. Okay, so that will be the benign cell, that will be the cancer cells. Okay, or the other way around. I think that these one are, the blue one are the benign and the red one are the cancer, if I remember well, because there's much more variability in the cancer cell, if I remember well. Okay, so let's test it. So we are going to use, for example, random forest classifier, but not on the whole dataset, but just on the dataset of the PCA dataset and only the 2 first features. So rather than considering the 30 features at the beginning, we just use just 2, and only with the 2 you see that the result will be quite good, in fact. Okay, from scikit-learn ensemble imports random forest classifier. I'm going to create my classifier, which will be a random forest classifier. The number of estimators is going to be 100, and the max depth to be 5. Okay, I'm going to fit it, classifier.fit the X PCAs and the Y, and I'm going to print what is the result using the testing dataset. So X test PCAs. So I'm going to transform the datasets, the testing datasets that I have, which is in the normal features. I'm going to transform it via the PCA. I'm going to select the two first column and see what the classifier is doing. Okay, PCA.transform X test, and I'm going to print the score. So print CLF.score. So I'm going to use X test PCAs. I only select the two first columns, so all the rows and all the columns up to index 2 without including index 2. And the good answer, the target is Y test. Okay. So if you do that, yeah, you see that building that thing with just the two first features of the PCAs, it's already 93% accuracy. So it's not bad at all, even considering there are very few information that could look like very few information. Rather than considering 30 features, you just consider the two of them, or at least two of the PCA one, and already have a good answer. Okay. So we are arriving at the end of this workshop. Some concluding remark. So we have used extensively Jupyter Notebook. I hope you like this tool. I hope that you will use it again. It's a very cool project that is used more and more, and I know some of the people in the project, and it should be cool to use them. They are great people. We explore the functionality of NumPy and Matplotlib libraries. Once again, even if you don't do machine learning after that, but you want to use Python for your work, I think NumPy and Matplotlib are great tools for you. We studied supervised learning with the two fundamental subfields, that is to say classification and regression. I put a huge stress of avoiding, underfitting is quite easy to avoid, but overfitting is much harder thing to avoid. So please keep in mind that you need to put aside at the very beginning testing dataset and assess the performance of your model at the very end using this one. You will be sure of what you are doing, and when you assess that performance of the model, you'll be sure of what you are doing. We investigate the scikit-learn structure and discuss how to find information in the documentation pages, which is very important for yourself to learn by yourself. Is the way we do it. We go into the documentation, we look at the question online to have answer, and we briefly discuss about some unsupervised learning algorithm at the very end. So that's the big summary: classification, regression, k-means, the three huge type of subfield that we have covered in that workshop. Some books. So yeah, so this book here is very cool. Is written by, I think, a French guy, or maybe Quebec, from the Quebec, I don't know. It's very close from what you are doing. So basically it's with Python, using scikit-learn, and there is some code in Python. You have to write that down. It looks like the same approach that we have in that workshop. You won't be lost if you use that book. There's also talking about TensorFlow. TensorFlow are about neural network. I haven't talked about that in that workshop because it's a little more advanced, but still you need to know everything that I've said today in order to have a good way to approach those kind of algorithms, neural network, which are very used today for good reason, because they are very good application, but sometimes they are kind of used. It's very heavy to use, a very heavy algorithm. It's very computer consuming resources. So be sure not to use neural network for very basic application. Try to use simple algorithm like the random forest, decision trees, especially in those kind of application. I mean, neural networks are very good for like recognizing an image, the image of the cat or the dog or things like that. Not that much for other application, or maybe it's too much, too heavy algorithm for that. But if you want to have a deeper look in what is deep learning, you can have a look at this guy. So it's making some example. This guy here is a little bit more mathematical. You will have more in depth into the algorithm that are used mathematically. If some of you are more mathematically and kind of still wanted to have more information, more precise information about the algorithm, you can have a look at this algorithm, this book here. And this book is the very huge book of deep learning. So if you are dedicated to deep learning, please look. That's basically the Bible. So you can go. There's two ways of having it. The first way, you go on Amazon and can buy it for like, I don't know, $50 or something, or you can go on the website of the author and just download it directly. So I don't know if it's legal or not. I think it is, because if the author themselves put it online. So if you want just have the PDF, just have a look on their webpage, you will find it. So that's maybe interesting for you. So I haven't talked about all the algorithm. I don't know all of them. So maybe here is a very interesting slide when you're kind of you don't really know what you do. Is the kind of a map of what you want to do. So here, if you have more than 50 samples, then you can answer that question. If you have less, then you need more data. Are you doing category? Yes, so if the data are available, so if you are supervised or unsupervised learning, then it's a classification or clustering. You can find my k-means over here. So basically you can navigate into that map to have the algorithm which is specific to your application, and have a deeper look into the scikit-learn documentation and example online, and to have that. So I hope we cover our goal. So my job here was to give you the basic knowledge, to have the good practice into machine learning. Of course, I cannot teach everything about machine learning, and of course, maybe it's more interesting to learn by yourself using that resources. Google is your big friend, or whatever search engine you are using. Stack Overflow and Cross-Validated are websites where you can ask questions, have answer, and most of the time somebody else asks the question, had the same question that you did before, so you already have the community answering questions. So it's a very huge tool. I mean, I've learned so many things using those two websites. This guy here, this website is for Stack Overflow is more for programming in general, and Cross-Validated is more for machine learning specific. So if you have just Python question in general, Stack Overflow is a great tool. More specific to machine learning, Cross-Validated. You have the books, and in the end, hopefully you will have your model which is working. And I thank you for following this video version of the workshop. I hope you like it. Don't hesitate to send me some mail if you are for some if you have questions or remarks about the workshop. I'll be happy to read more about you, and say to you bye, and hope to see you next time, maybe in another workshop.